Hello friends, here in this video we will see a problem on SFD and BMD for the beam as shown in figure. Here is the diagram. It is mentioned in the question that draw axial force, shear force and bending moment diagrams for the beam loaded as shown in figure. So they have given us this diagram. Now when we look at this beam, it will be called as beam A, B, C, D, E, F, G. Now just by looking at this beam, we can say that there is a point load acting whose value is 20 kilonewton at B and its distance is from point A 3 meters. Next at point D there is a couple acting whose value is 10 kilonewton meter. After that there is UDL from point E to point G having intensity 20 kilonewton per meter. Next at point G there is a load acting which is inclined. Its inclination is 30 degree with horizontal and the value of load is 50 kilonewton. Next after this, if I look at the supports, this beam is supported at point A, point C and point F. At point A this support is hinged. This is the symbol of hinge support. At point C it is roller support and even at point F it is roller support. Apart from that, they have said in this problem indicated that point E is internal hinge. Now because of internal hinge, what happens that we are going to see in the further part of this problem. And as while reading the question, we have to even draw axial force diagram here. Apart from shear force and bending moment diagrams, we even have to draw the axial force diagram. So with the question understood, let us try to get the solution to this problem. Now in the solution part, we will divide the solution into three simple steps. The first one will be calculation of support reactions, second shear force calculations and third bending moment calculations. So starting with the first step, calculation of support reactions. Now for the support reactions, here there is a hint in this problem. Whenever they give us internal hinge, at that time we have to remember that this beam will be divided at the internal hinge. That is, the beam will be divided into two parts. So I'll say that when internal hinge is present at point E, then portion A, B, C, D and E, this will be the left hand portion of the beam. Then E, F, G, that will be the right hand portion. So the beam will be split into two parts at the internal hinge. If suppose internal hinge was not present, then in that case for the calculation of support reactions, we would have taken the entire beam as a whole and calculated the support reactions. But since internal hinge is present, we have to divide the beam into two parts at the internal hinge. So now I will be dividing this beam at the internal hinge. Then at the same time, here there is hinge support. Whenever there is hinge support will offer angular motion in angular direction. That is, the beam will not move in horizontal or vertical direction, but it will be moving in angular direction. So there will be horizontal and vertical reaction at point A. Then if there is roller support, in that case there will only be vertical reaction, because at the roller when the load acts, the beam can move in horizontal direction and this roller support also offers some angular motion. So there will be only vertical reaction, that is, the beam cannot move down at point C. Then again there is roller support at point F, so there will only be vertical reaction. So at hinge support there are two reactions, horizontal, vertical. At roller support there is only one reaction, that is vertical. So here when I am splitting the beam, I replace the hinge and roller support with the reactions. Let us see how it is done. So now here I have split the beam into two parts at internal hinge point E. I'll explain what I have done here. Here as internal hinge is there at point E, so I have drawn the free body diagram of beam ABCDE. So this is FBD for beam ABCDE, the first part, and the second part is FBD for beam EFG, the remaining part. Now I'll explain what I have done here. If I look into part A, B, C, D, E, at A there is hinge support. So at hinge support there will be two reactions, one horizontal reaction at point A, then vertical reaction at point A. Next 20 kilonewton load is as it is. After that at C there is roller support, so only vertical reaction, so there is vertical reaction R suffix C. Then at D there is a couple acting 10 kilonewton meter. After that at internal hinge, here what we have done is, since at internal hinge there won't be, here internal hinge is there, so there is no reaction present, but here I am introducing two reactions. That is, first if I consider EFG, in that there is RE which is acting upward at E portion, point E, which is in this ABCD portion of the beam. This RE is acting downward, and here the reaction RE is acting upward. So when the beam combines, it means there is no reaction at the internal hinge because it is not supported at this end. So at internal hinge, whenever we are splitting the beam, we have to show the reactions in this form. One reaction should act downward, other should act upward, values will be same. and they will cancel out one another. Next, since it is internal hinge, there will be horizontal reaction also. So horizontal reaction at E, one I am showing towards left, and on the other part of the beam at point E, I will show horizontal reaction towards right. So that again the horizontal reaction also gets cancelled out, and we don't have any reaction at point E, which is the internal hinge. So this is the way the beam should be split. Then at point G, there is 50 kilonewton inclined at 30 degree. That I have resolved. So G will have the load which is acting 50 kilonewton. We'll have two components. First horizontal component, then other the vertical component. Inclination is with horizontal, so horizontal component will become cos and the vertical will be sine. So horizontal component is 50 cos 30, vertical component is 50 sine 30, and I'll even write their values here. 50 sine 30, that is 25 kilonewton. 50 cos 30, that is 43.30 kilonewton. Now once we have understood this, that is we have reached at this stage where I have split the beam into two parts. Now we have to calculate the reactions, and if we see the beam as it is supported at A, at C, at F, we need to find RA, RC, RF values. So first, for what I'll do here is, if I look in portion A, B, C, D, E, here I'm having reaction at A, reaction at C, and even RE. So there will be three unknowns here, and at the same time there is HA and HE. So if I look into this portion of the beam, there is no horizontal forces present here, only reactions are there, HA and HE. But if I look into the other portion of the beam, here horizontal reaction is there, also horizontal force is present, so I will be able to calculate horizontal reaction from here. So it is better to start with the FBD for beam EFG first, find the reactions here, and then go on to the next part, that is ABCDE. So let us get started here. I am considering portion EFG of the entire beam ABCD EFG. Now first I'll find the horizontal reaction, and for that I'll use the condition of equilibrium, because horizontal reaction will be required to draw axial force diagram. In this problem they have said also draw axial force diagram. So first I'll write down the equilibrium condition, summation of Fx is equal to 0, where rightward force is positive and leftward force is negative. So if we look into portion EFG, HE is acting towards right, so positive, so therefore HE is positive. 50 cos 30 is acting towards left, so negative, minus 50 cos 30 is equal to 0. There are no other horizontal forces present, so from this I'll get the answer of HE. 50 cos 30, that gives me the value as 43.30. This will be negative. If I send it onto the other side, it becomes positive, so 43.30 kilonewton. This is the value of horizontal reaction at the internal hinge point E. Next, after this I even need to find out the values of RE and RF here. So for RE and RF, as both are vertical, I'll use the condition of second condition of equilibrium, that is summation of Fy is equal to 0. Summation of Fy is equal to 0, where upward forces are treated positive and downward forces are negative. So we have RE plus RF, that is the reaction at point E and point F, RE plus RF, then minus 50 sine 30 because it is acting downward, and that 50 sine 30 has a value of 25, so I'll write down minus 25. Next, there is even UDL present from E to G, so this UDL will be converted into point load, that is 20 into 3 meter, and that acts down, so minus 20 into 3 is equal to 0. So from here I'll get RE plus RF is equal to, this will be 85, and that will be equation number 1 for us. Next, now after getting equation number 1, here we want the values of reaction. So if I take the moment at point E, I'll get RF. If I take the moment at F, I'll get RE. So anyhow we are correct. Either we can take moment at E or point F. Here I'm taking the moment at point E. So I'll write down the next condition of equilibrium. Summation of moments about point E, that is equal to 0, where clockwise moments are treated positive and anti-clockwise moments as negative. So therefore we have here point E is there. If I take the moment of RF will produce anti-clockwise moment since it is acting upward, and when I'm taking the moment it comes in anti-clockwise direction at point E. So minus RF into 2. Then 50 sine 30, that is 25, it is acting downward, and when I take the moment at point E it is clockwise, so plus 25 into 3. Then there is UDL whose value is 60, that is it is 20 into 3, and UDL will be the UDL which I convert into point load will be acting downward, and when I am taking the moment at point A it will be clockwise. So this UDL will be exactly, when I take the point load, it will be acting at half of 3, that is 1.5 from point E. So it will be 20 into 3 into 1.5 and producing clockwise, so positive. So plus 20 into 3, that is UDL is converted into point load. Then the distance is half of 3, that is 1.5, and from this that is equal to 0. And here if I go on calculating, I'll get the answer of RF as it is 82.5 kilonewton. Then after getting this RF value, I'll put it in equation number 1. So therefore put RF is equal to 82.5 kilonewton in equation number 1. So therefore RE will be equal to 85 plus RF, when it goes on to other side becomes minus RF, so minus 82.5. So from this I'll get the value of reaction at E, and the answer is 2.5 kilonewton. So here I have calculated the first part in this problem, that is here we have found out horizontal reaction at E and vertical reaction at E and F respectively. So now after getting the reactions HE, RE and RF, we can say that we have finished the portion EFG of the beam, that is this much is what we have to find. Now we'll concentrate here, that is the other part of the beam, and we will be finding here HA value, RA and RC. So I'll write down considering FBD of portion ABCDEF of beam of the complete beam, and it will be only up to point E. Now here also horizontal reaction is present at A, at E, so I'll say that using the first condition of equilibrium, summation of Fx is equal to 0, rightward force is positive and leftward force negative. So therefore we have HA acting towards right, HE acting towards left, so minus HE, Apart from this, no horizontal forces are present in this part, so this is equal to 0. Therefore HA minus HE value is 43.30, it's equal to 0. So therefore the horizontal reaction at A will be 43.30 kilonewton. Next, summation of Fy is equal to 0, where upward forces are treated positive and downward forces are treated as negative. I am using summation Fy because we have to find Ra and Rc value. So Ra, it is acting upward, positive. Rc is upward, positive. So Ra plus Rc then this 20 kilonewton force is acting downwards, so negative, minus 20. Next, here Re is also present. This Re will be acting downward, so minus Re. 10 kilonewton meter, it is a couple, so it cannot be used in the calculation of forces. So this 10 kilonewton meter won't be used here. We want only forces. So that is equal to 0. Hence Ra plus Rc minus 20 minus Re value is 2.5 is equal to 0. So from this, if I calculate, I'll get Ra plus Rc as 22.5, and this I'll keep it as second equation. Next, if we want to calculate the value of reaction at C, I'll take the moment at point A. If we want to calculate the value of Ra, we have to take the moment at point C. So in whichever case we are correct, so first I'll take the moment at point A to get the value of Rc. So I'll use the next condition of equilibrium, that is summation of moment about point A is equal to 0. The convention is clockwise moments treated positive and anti-clockwise moments as negative. So therefore here we have Rc which is acting upward, and when I take the moment of this Rc at point A, it comes out to be in anti-clockwise direction, so minus Rc into 4. Then 20 kilonewton will produce clockwise moment at point A, so plus 20 into 3. Then Re will also produce clockwise moment, so plus Re into this total distance is 5. Next, also there is couple present at point D which is 10 kilonewton meter, and this is, as it is clockwise, it will directly be considered positive, so I'll write the value plus 10. Apart from this, no other forces are acting, so this will be equal to 0. Therefore minus 4 Rc plus 60 plus Re value, which is 2.5 into 5 plus 10 is equal to 0. On calculating, I'll get the answer of Rc as, it is 21.25 kilonewton, 21.25 kilonewton. Next, after getting Rc, I'll put its value in equation 2 to get RA. And here we have to see that when I was taking the moment from RE, that is at point A, RE into the distance is 6. So here I have written RE into 5. Actually this is RE into 6. So this is 2.5 into 6, and this will give me the same answer, that is 21.25 kilonewton. Next I'll say that put RC is equal to 21.25 kilonewton in equation second. So from that RA will be here plus 21.25 is equal to 22.5. So therefore RA value will be 22.5 minus 21.25, and that gives me an answer as 1.25 kilonewton. So here we have found out the reactions. That is, we have calculated the value of HA, RA, RC, RE and HE. So we have completed this part of the FBD for beam ABCDE. Previously we have completed FBD for EFG, and here I can say that the entire beam which is given in the problem, for that we have found out the reactions at each and every locations. Now here with this we complete the step number 1. Then we have to go on to step number 2, that is shear force calculations. And for shear force calculations we have to use the sign convention first. So any force which is acting to the left of section in upward direction, to the right of section in downward direction, both are treated positive. Then any forces which are acting to the left and downward, to the right and upward, are treated as negative. So now here the second step is shear force calculations, where I have given the sign convention. Any force which is acting to the left of section in upward direction is positive. Force which is acting to the left and downward, negative. Next, a force which is acting to the right and downward, positive. Then to the right and upward, that is negative. After doing this, here on this beam diagram which they have provided, I'll mark the reactions so that it helps us out in the problem. Now for shear force calculation we have to just take the vertical reactions. RA value 1.25 kilonewton. RC value 21.25 kilonewton. Next, RF value, it was 82.5 kilonewton. Now here I have written all the reactions. In shear force calculation, first I'll calculate shear force at point A, and for that I'll take the section very close to point A, that is at this location. So when I'm taking the section very close to point A, on the left hand side of this section we are having RA acting upward, so that will be, as per the convention, it will be positive. Shear force at point A is equal to plus 1.25 kilonewton. Then SF at point B. Now this value of shear force which is at A 1.25 will remain constant up to the left of B. That is, if I take the section to the left of B, then also I have only single force on left hand side, that is 1.25 positive value. But if I take the section to the right of B, then the shear force value will change and it is downward. So here we have 1.25 upward and 20 downward. So on the left hand side, upward force is positive, downward force is negative. So that is plus 1.25 minus 20 and that gives me an answer as minus 18.75 kilonewton. Then this value of shear force will be constant up to the left of C, that is taking the section to the left, this shear force will be constant. But when I take the section to the right of C, then the shear force value will change because of RC. So we have SF at point C is equal to plus 1.25 minus 20, that is RA is upward, so plus 1.25 minus 20 and plus RC because it is to the left of the section and upward, so positive, that is plus 21.25. On calculating this, I'll get the answer as plus 2.5 kilonewton. After getting the shear force at point C, between point C to D there are no forces present, so whatever shear force we are getting at point C, same will be the value at point D. Is equal to, similarly there are no forces from D to E, so whatever shear force we get at point C, same will be the value at D and same will be the value at E. It means in portions C, D and E the shear force remains constant. So that is plus, I'll write down SF at point D is equal to SF at point E. Answer is plus 2.5 kilonewton. Then at point F, I'll get two values of shear force. First, by taking the section on the left of point F, so SF at point F will be equal to, here we have the value RA 1.25, which is plus, then minus 20 plus 21.25. Then after reaching here, there is even UDL present in this portion, that is up to 2 meter, because I am taking the section very close to point F, so the distance can be considered 2 meter. So the UDL is acting over this distance and the value is 20. This UDL, when I convert it into point load, will act downward, and any force on the left hand side of the section in downward direction is negative, so that will be minus 20 into 2. UDL I have converted into point load. So SF at point F, I will get the value as minus 37.5 kilonewton. We'll get another value at point F, that is, now I'll take the section very close to point F on the right hand side of F, where we will even have this 82.5 kilonewton acting upward. So up to the left of F the forces are minus 37 0.5 kilonewton. Then here I have RF, which is acting upward on the left hand side section, so positive, that is plus 82.5 kilonewton. So from this I'll get the value of shear force at point F as plus 45 kilonewton. Then after that only point G is left, so therefore shear force at point G will be equal to, now I'll take the section very close to point G. So just on the right hand side of G I'll have a single force, which is the component of 50, which is inclined at 30 degree, that is 50 sine 30, which is on the right hand side of the section, and on the right hand side if the force is downward, that is positive. So SF at point G is equal to 50 sine 30, and that is plus 25 kilonewton. So here I have found out the shear force values at each of the points. After getting these shear forces, we need to draw the shear force diagram, and for that I'll have to draw the beam again. So I'm drawing the beam diagram once again because we have to draw the diagram as well. So now here as I'm drawing the diagram, now after I have completed the beam diagram as mentioned in the question, we have to even draw axial force diagram, and for that axial force I'll require the horizontal reactions which we have found out, that is the horizontal reaction at point E, it is 43.30 kilonewton. Similarly, the horizontal reaction at A, it was also having the same value. It means the horizontal reaction is constant throughout. So the axial force diagram is a positive diagram. So for that, first I'll draw a line. which is showing 0 kilonewton force, and the value of reaction, which is horizontal, we get the value as plus 43.30, so it will be above this line because positive forces are shown above the line. So this diagram is entirely positive. And this is AFD, the axial force diagram, which was asked in this question. Now, below the axial force diagram, we need to draw the shear force diagram, that is SFD. And for that shear force diagram, we require the shear force values. Again, this is 0 line, 0 kilonewton force. Now we'll plot the shear force values. At point A, the value of shear force is plus 1.25 kilonewton, so above the line. kilonewton. Now this value of shear force remains constant from A to B unless there is this 20 kilonewton force, so the value remains constant from A to B. Then at point B, the value of shear force is minus 18.75, so negative means it goes below this 0 line, minus 18.75. Then this value will remain constant from B to C unless there is reaction from C, so here this will be constant, 18.75 kilonewton. Then it goes into positive, that is after minus 18.75 at point C, the value is plus 2.5 kilonewton. Now, as I have explained previously also, between points C, D and E there are no forces present, so this shear force value will remain constant from C, D and up to E, that is SF at point C was plus 2.5, so at D and E also it will be plus 2.5. Next, after reaching point E, at point F we have two values of shear force. The first value is minus 37.5, minus means it will go below this line, minus 37.5. Then as there is UDL from E to F, shear force will be an inclined line, so joining them it goes into negative minus 37.5, and the other value at point F is plus 45 kilonewton. So plus 45 means it will go into the positive region. Then at point G, the value of shear force is plus 25 kilonewton. So again this will be positive value above the line, plus 25 kilonewton. Then between F to G there is UDL, so shear force should be an inclined line, so joining 45 kilonewton and 25 kilonewton, this is an inclined line. Next I'll mark the sign here, this is positive, positive and positive here, this is negative. So this completes the step number second. That is, here we have drawn the shear force diagram SFD. So now here we have completed step number second, that is we have drawn the SFD and BMD. The SFD, that is shear force diagram, I have completed. Now I'll go into step number 3, that is bending moment calculations. Now for the bending moment calculations, here we need the sign convention first. If a moment is acting on the left hand side of the section in clockwise direction, on the right hand side of the section in anti-clockwise direction, both will be treated as positive. Then if the moment is in the left hand side of the section acting anti-clockwise, right hand side of the section acting clockwise, both are treated as negative. Now here I'll give some important hints. At first, shear the bending moment value at point A will be 0. Because it is hinge support, there won't be bending. Next, at point G, which is the free end, the bending moment will be 0. Now one important point, since point E is internal hinge, even at internal hinge the beam will be bending, so the bending moment at point E is 0. Here I'll write a special note here. An important note. Bending moment at internal hinge will always be equal to 0. So here I'll first write down moment at point E, which is the internal hinge, is equal to 0. Next, moment at point A, that is equal to 0 because it is hinge support, or I'll write down into the bracket that since it is simply supported, next, moment at point G will be 0. Since it is free end. Then after that we need to calculate the moment values at point B, at C, at D and at point F. So first starting with B. Moment at point B will be equal to, now here if we see at point A there is a reaction called as RA, reaction at A. Now when I take the moment at B, this RA will be coming into clockwise direction and it is to the left of B. So clockwise moment on the left hand side of the section is treated positive. So this is plus RA into 3. RA value is 1.25. So moment at B, that will be plus 3.75 kilonewton meter. Next, moment at point C, this will be equal to RA into 4 and it is clockwise, So plus RA into 4. Then this force 20 Newton, 20 kilonewton, 20 into 1 is anti-clockwise. So on the left hand side of the section, anti-clockwise is negative as per the convention. So minus 20 into 1. Here I'll put the value of RA. Moment at point C is minus 15 kilonewton meter. Next, moment at point D. For this point D, again, just before calculating the moment, I'll write a note here for point D. So here I have written a note that if a couple is acting at a point, then at that point there will be two values of bending moment. So if we see here for the given beam, at point D a couple of 10 kilonewton meter is acting. So here at point D we are going to get two values of bending moment. First, by taking the section to the left of D, where this 10 kilonewton meter couple will not be there. Then taking the section to the right of D, where this clockwise couple will be there. So first, neglecting this couple, I'll calculate the bending moment at D. It will be equal to RA will produce clockwise moment at D. Distance is 5 meter from A to D. So RA into 5, that is plus RA into 5. Next, 20 kilonewton will produce anti-clockwise moment in the left side, so negative minus 20 into 2. Then here there is reaction at C, RC. It will be producing anti-clockwise moment. It will be producing clockwise moment at point D, so that will be clockwise is positive on the left side, plus RC into 1. I'll go on putting the values. RC is 21.25. From this I'll get the value of bending moment at D, and my answer is minus 12.5 kilonewton meter. So now here I have got moment at D by taking the section to the left of D, that is here I am not considering the couple by taking the left side section. Now when I am taking the section to the right of D, this couple will also be there. So again second value of moment at point D will be equal to, up to the left the value is minus 12.5, it will remain same. And when I am taking the section on the right hand side of D, to the left there is clockwise couple, so clockwise couple to the left is treated positive, and that will be plus 10. So the moment at D, the other value will be minus 2.5 kilonewton meter. Next, only moment at F is left. So therefore, moment at point F will be equal to, this can be solved by taking this right hand side portion, only F to G. So 50 sine 30, it is producing clockwise moment on right hand side, Clockwise moment on right hand side is negative. So minus 50 sine 30 into 1. Then here F to G portion, it also has the same value of UDL, 20 kilonewton per meter. So that will be 20 into 1, the UDL into point load. So I've converted UDL into point load, and it will be acting at half of 1. Then because of the UDL, the moment which will be produced, that will be clockwise direction on right hand side. So again this will be negative. So here I will be getting the value as minus 12.5 kilonewton meter. Now I have calculated the moment at each and every location, but if I see in this diagram, that is the shear force diagram, there is one point where the shear force is changing sign, as we can see here, from 2.5 to 37.5, which is negative. So here it is crossing this zero line. It means at this point the shear force value is 0. So here SF is equal to 0. So wherever we are getting the SF value as 0, there the bending moment will be maximum. So I will project this point downward. So at this location I'll get the maximum value of bending moment. But the thing is, we do not know this distance, that is where this shear force is 0. So I'll assume that from point E, this distance is x. So ultimately from point F, the distance will be 2 minus x. This much distance will be 2 minus x. So by using similarity of triangles, both are right angle triangles, I'll get this distance x. So next I'll mention that calculations for maximum BM, that is maximum bending moment, and for that I'll draw the triangles. So we will be calculating the distance x with respect to point E. So here I'll write down, therefore by similarity of triangles, I am considering this triangle, so its height is 2.5 divided by its base, which is x, and here the height of this triangle is 37.5. Its base is 2 minus x. This will be cross multiplied. into 2, that becomes 5, minus 2.5x is equal to 37.5x. So on calculating this, I'll get the answer of x, which comes out to be it is 0.125 meter from point E. That is, here I have found out that shear force is 0 at a distance of 0.125 meter from point E. So from F also I'll write down, from F that will be 2 minus x. So therefore this 2 minus x value will be 2 minus 0.125, that is 1.875 meters, and that is from F. So I'll show these values onto the diagram. X is 0.125 meters and 2 minus X, that is at a distance of 1.875 meters, the value of this. Now I will have to calculate the maximum bending moment at this location. So therefore, for that case, I'll project the same distance onto this diagram, that is the beam diagram, and here this distance is with respect to point F, that is this is the location where shear force is 0, 1.875 meter. Here I have to find the value of maximum bending moment. Therefore, maximum bending moment is given by m suffix max is equal to, here if we see 50 sine 30, that is 25 kilonewton, is producing clockwise moment, so it is on the right hand side of the section. So clockwise on the right hand side is negative, so minus, I'll directly write the value of 50 sine 30, which is 25 kilonewton. So 25 into the distance between this section and point G is 1.875 plus 1, that is 2.875. Then here there is also reaction at F, RF, and this RF will be producing anti-clockwise moment. So on the right hand side anti-clockwise is positive, so RF into 1.875, which is plus RF into 1.875. Then there is UDL in this portion from 1.875 to 1 meter, and the intensity is 20. So UDL into point load, that is 20 into 2.875, and when we take the moment, it will be acting at half of 2.875 to the right of the section, that will be producing clockwise moment, so negative. Now I'll put the values here of RF. This will be minus 71.88 plus RF value 82.5, and this entire term when I calculate it will be 82.66. So therefore the maximum bending moment comes out to be plus 0.15 kilonewton meter. And this maximum bending moment, as we see, it will be for the portion EFG of the beam. And now I am going to plot that. Again, zero line. Moment at point A is 0. I'll put the values at A. At B it is plus 3.75. Then at C the value is minus 15 kilonewton meter. Then at D there are two values, first minus 12.5, then minus 2.5 kilonewton meter. At E the value is 0. So for this much portion I'll draw the bending moment diagram first. 3.75 kilonewton meter. Then at C the value is minus 15, so downward. Then here it is 12.5 at point D, the first value. Other value is 2.5 minus 2.5, so downward. Then at E the value of bending moment is 0. It is on 0 line because internal hinge is there, so the bending moment is 0. Now I'll connect the points from A to B. As there is no load between A to B, shear force was straight line, bending moment will be an inclined line. Next, from B to C there is no load, shear force is straight line, bending moment will be inclined line. So from plus 3.75 it will go into minus 15 kilonewton meter. Then from C to D there is no load, so shear force was a straight line, bending moment will be inclined line. So from minus 15 to minus 12.5 kilonewton meter. Then at D there are two values, from minus 12.5 to minus 2.5 kilonewton meter, and then finally from here up till 0. So this is the half bending moment diagram. This much region is plus and here it is minus. Next, after reaching here, at point F the value of bending moment was minus 12.5, so same level. Then at G the value is 0, and we have even found out the maximum bending moment where shear force was 0. This value is plus 0.5. kilonewton meter. Now I have to join them. From E to G there is UDL. So whenever there is UDL, shear force is an inclined line, bending moment will be parabola. So from point 0, that is point E internal hinge, up to 0.5 there will be parabola of increasing order. It will reach maximum value up to 0.15. Then this parabola will go into negative region, go on decreasing and reach up till minus 12.5 kilonewton meter. Then from F to G there is UDL, so again from minus 12.5 it will go up to 0 kilonewton meter, and I am drawing the parabola in this region in this way because it should show maximum value at 12.5. Otherwise if I am drawing it in this way, there can even be a point where the value will be maximum, that is greater than 12.5. so I have to show it in this way, and here this is positive and here it is negative. So this is the bending moment diagram. And here if we see, there are 2 points at which the bending moment is 0 at this location. BM is equal to 0, and even here at one location BM value is equal to 0. So these are called as point of contraflexures. So here we have drawn the axial force diagram, shear force diagram and bending moment diagram.